You know, when we think about the beginning of everything, we're really asking one of the most profound questions that humans have ever contemplated. How did we get here? How did anything get here? And when I say anything, I mean, well, literally everything. Every atom in your body, every star in the sky, every galaxy spinning through the cosmic dark, all of it somehow emerging from what we might call nothing. But what is nothing, really? It's harder to define than you might think. We tend to imagine nothing as this empty void, this perfect absence of anything at all. But even empty space, even what we call a vacuum, isn't truly empty. It's teeming with activity, with quantum fluctuations, with virtual particles popping in and out of existence so quickly that we can barely detect them. So maybe the question isn't how something came from nothing, but rather, what kind of nothing are we talking about? The story begins, as far as we can tell, about 13.8 billion years ago. Not with a bang, despite what we call it, but with an expansion. A sudden, rapid, almost incomprehensible inflation of space itself. In the first fraction of a second, and we're talking about time scales so small they make a blink of an eye seem like an eternity, the entire observable universe expanded from something smaller than a proton to something the size of a grapefruit. Then it kept going. This is inflation theory proposed by Alan Guth in the 1980s, and it's remarkable because it explains so many of the features we see in our universe today. The uniformity of the cosmic microwave background, the flatness of space on large scales, the way galaxies are distributed. All of it pointing back to this moment of incredible expansion. But what caused it? What was the mechanism? Well, this is where we enter the realm of quantum field theory, where the rules of everyday experience break down completely. We think there was a field, what we call the inflaton field, that was in a high energy state, and like a ball rolling down a hill, this field wanted to decay to a lower energy state. When it did, that decay released enormous amounts of energy, driving the expansion of space itself. It's a bit like, imagine you have a pot of boiling water, but instead of steam bubbles, you have bubbles of true vacuum expanding rapidly outward. Our entire observable universe might be just one of these bubbles expanding into something we can't even observe or understand. And here's where it gets really interesting, really mind-bending. If inflation happened once, there's no reason to think it only happened once. We might live in what cosmologists call an eternal inflation scenario, where new universes are constantly budding off, each with their own physical laws, their own constants, their own history. A multiverse vast beyond imagination, where every possibility is realized somewhere. But let's step back to our universe, our cosmic home. After inflation stopped, we had this hot, dense, rapidly expanding soup of energy and elementary particles, quarks and leptons and gauge bosons, all interacting in ways that we're still trying to understand. The temperature was it was so hot that atoms couldn't form. Matter and antimatter annihilating each other in flashes of pure energy. Somehow, though, matter won. There was a tiny asymmetry, maybe one extra matter particle for every billion matter-antimatter pairs. And when the annihilation was over, when the universe had cooled enough, that tiny excess became everything we see today. Every star, every planet, every galaxy, all of it built from the survivors of that cosmic battle between matter and antimatter. This is called baryogenesis, the creation of matter, and it's one of the great unsolved problems in cosmology. We know it happened because here we are, made of matter. But we don't fully understand how or why. There are theories involving violations of charge, parity symmetry, involving phase transitions in the early universe. But we're still working on it. As the universe continued to expand and cool, the first atoms began to form. Hydrogen, mostly with some helium and traces of lithium. This was about 380,000 years after the Big Bang, during what we call recombination. Before this, the universe was opaque to light, like being inside a dense fog. But when the electrons combined with nuclei to form neutral atoms, suddenly light could travel freely. The universe became transparent for the first time. That light is still with us today. It's the cosmic microwave background radiation discovered by Arno Penzias and Robert Wilson in 1965. Quite by accident. They were trying to eliminate noise from their radio antenna and kept picking up this persistent signal from every direction in the sky. What they'd found was the afterglow of creation itself, stretched and redshifted by billions of years of cosmic expansion. And when we look at that cosmic microwave background in detail with satellites like COVE and WAP and Planck, we see tiny variations in temperature, tiny ripples in the fabric of space-time. These ripples, probably quantum fluctuations, stretched to cosmic scales during inflation, became the seeds of all structure in the universe. Galaxies, galaxy clusters, the cosmic web itself, all of it growing from these primordial perturbations. But the universe at this point was dark. There were no stars yet, no galaxies, just vast clouds of hydrogen and helium drifting through the expanding cosmos. We call this the cosmic dark age, lasting for tens of millions of years. Gravity was working, though, slowly pulling matter together, concentrating it in regions where those early ripples were slightly denser. Eventually, these concentrations became dense enough, hot enough for nuclear fusion to begin. The first stars ignited, massive and short-lived, burning through their fuel in just a few million years. When they died spectacularly as supernovas, seeding space with the first heavy elements, carbon, oxygen, silicon, iron, all of it forged in the nuclear furnaces of stellar cores and scattered by stellar death. This was the end of the Dark Age, the beginning of what we call cosmic dawn. And it's a story we're still piecing together, using the most advanced telescopes we've ever built. The James Webb Space Telescope is showing us galaxies that formed when the universe was just a few 100 million years old, giving us glimpses of that first generation of stars and the early formation of structure. These first galaxies were different from what we see today. Smaller, more chaotic, actively forming stars at rates that would be almost unimaginable in our current cosmic epoch. The Hubble Space Telescope showed us some of these early galaxies, but Webb is revealing them in unprecedented detail. Galaxies that formed just 400 million years after the Big Bang, already massive, already complex, challenging our understanding of how quickly structure can form in the early universe. And as these galaxies evolved, something remarkable happened. The heavy elements produced by the first generation of stars began to accumulate. Second-generation stars formed with more complex chemistry. Planets began to form around them. And for the first time in cosmic history, the ingredients for complexity, for life began to come together. But we're getting ahead of ourselves. Let's think about what it means for the universe to expand from nothing. Because this idea, this concept of exhalation, it troubles some people. How can something come from nothing? Doesn't that violate the most basic principles of physics? Well, maybe. Or maybe our intuitions about nothing are simply wrong. In quantum mechanics, the vacuum isn't empty. It's full of quantum fields in their ground state, constantly fluctuating, constantly creating particle-antiparticle pairs that exist for the briefest moments before annihilating each other. These are virtual particles, and they're not quite real in the sense we normally think of reality, but their effects are measurable. The Casimir effect, for instance, where two metal plates in a vacuum will actually attract each other due to these quantum fluctuations. So maybe the universe didn't come from nothing in the philosophical sense, but from something more like a quantum vacuum, pregnant with possibility. The physicist Frank Wilczek describes it beautifully when he talks about the universe as a kind of crystallized nothing, where the symmetries of empty space have been spontaneously broken to create the rich structure we see around us. Before we continue exploring these deep questions about existence and creation, I'd like to ask you to subscribe to the channel to help me reach the first 1,000 subscribers here. The purpose of this channel is to help you fall asleep with high-quality knowledge, right? It doesn't cost anything. Just hit that subscribe button. Now, there's another way to think about the beginning of everything, and that's through the lens of what physicists call symmetry breaking. In the earliest moments of the universe, when temperatures and energies were unimaginably high, the fundamental forces we see today, the strong force, the weak force, electromagnetism, even gravity, they might have been unified into a single, more fundamental force. As the universe expanded and cooled, these symmetries began to break. First, perhaps, gravity separated from the other forces during the Planck epoch when the universe was just 10 to the minus 43 seconds old. Then, as cooling continued, the strong nuclear force decoupled. Later still, the electromagnetic and weak forces separated, an event we can actually recreate in particle accelerators today. Each of these phase transitions, because that's really what they were, like water freezing into ice, released energy and created the distinct forces and particles we observe today. The Higgs mechanism discovered at the Large Hadron Collider is thought to be responsible for one of these transitions, the one that gave mass to particles like electrons and quarks. But here's the thing. Here's what keeps cosmologists awake at night. We can trace the evolution of the universe back to about 10 to the minus 35 seconds after the beginning. Before that, the energies involved are so high that our current theories simply break down. We enter what physicists call the Planck era, where quantum effects of gravity become important, where space and time themselves might have been different, might not have existed at all in any sense we can understand. This is where we need a theory of quantum gravity, something that can reconcile Einstein's general relativity with quantum mechanics. String theory is one candidate, suggesting that the fundamental constituents of reality are tiny, vibrating strings rather than point particles. Loop quantum gravity is another approach, proposing that spacetime itself is quantized, made up of discrete units smaller than anything we can currently measure. Some theories suggest that time itself might be emergent, arising from more fundamental processes. Others propose that our universe is just one slice of a higher dimensional reality, like a shadow cast by objects we can never directly perceive. The episodic scenario suggests that our Big Bang was actually a collision between higher dimensional membranes or branes in a space with more than our familiar 3 dimensions. And then there are the truly speculative ideas. The notion that consciousness itself might play a role in the creation of reality, or that the universe is a kind of hologram, where all the information about a 3-dimensional space is encoded on its 2-dimensional boundary. These ideas push at the very limits of science into territories where mathematics and philosophy begin to merge. But let's return to something more concrete, more observable. After those first few 100 million years, as the first generation of massive stars lived and died, the universe began to look more recognizable. Smaller, longer-lived stars began to form, stars like our Sun. And around these stars, in the swirling disks of dust and gas, planets began to coalesce. This process of planet formation it's violent and chaotic and beautiful. We think it begins with tiny dust grains sticking together through electrostatic forces, growing into pebbles, then rocks, then asteroids. Gravity takes over as objects grow larger, and eventually you have planetesimals colliding and merging, building up the rocky cores of planets. For planets close to their star like Earth, this process creates worlds that are initially molten, constantly bombarded by asteroids and comets. The early Earth was a hellscape of magma oceans and toxic atmospheres. But gradually, as the bombardment slowed and the planet cooled, something extraordinary happened. Water vapor in the atmosphere condensed, falling as rain for perhaps millions of years, creating the first oceans. And it's in these early oceans that one of the most profound mysteries of our cosmic story unfolds: the emergence of life itself. We don't know exactly how it happened. This transition from chemistry to biology, from dead matter to living systems capable of reproduction and evolution, but we can piece together some of the puzzle. The early Earth was a very different place. The atmosphere contained no oxygen. That came later, produced by the first photosynthetic organisms. Instead, there was methane, ammonia, hydrogen sulfide, water vapor. Lightning crackled through these primordial skies, and ultraviolet radiation bathed the surface without the protective ozone layer we have today. In 1953, Stanley Miller and Harold Urey tried to recreate these conditions in a laboratory. They filled a flask with water and gases thought to represent the early atmosphere, then subjected the mixture to electrical sparks to simulate lightning. Within days, they found amino acid, the building blocks of proteins forming spontaneously from simple chemical precursors. It was a remarkable demonstration that the organic molecules necessary for life could arise naturally from non-living matter. But making amino acids is one thing. Creating a living, self-replicating organism is quite another. There's something we call the RNA world hypothesis, which suggests that before DNA and proteins, there were RNA molecules that could both store information and catalyze chemical reactions. RNA is fascinating because it can do both jobs that are now split between DNA and proteins in modern cells. It can store genetic information, and it can act as an enzyme, speeding up chemical reactions. Some scientists think that early life was based entirely on RNA, with DNA and proteins evolving later as more efficient specialists. But even this leaves questions unanswered. How did the first self-replicating RNA molecules arise? How did they become enclosed in cell membranes? How did the genetic code, this almost universal language that translates RNA sequences into protein sequences, how did that evolve? These are deep questions, and we're still working on them. Some researchers are exploring the idea that life might have begun around hydrothermal vents on the ocean floor, where hot mineral-rich water provides both energy and the right chemistry for organic synthesis. Others think that clay minerals might have served as templates, helping to organize and concentrate organic molecules. There's even the possibility that life didn't begin on Earth at all, but arrived from space, perhaps carried on meteorites or comets. This is called panspermia. And while it doesn't solve the ultimate origin of life, it does expand the possible venues where life might first have emerged. What we do know is that once life got started, once that first self-replicating system began, evolution took over. And evolution it's one of the most powerful forces in the universe. Given enough time, it can create incredible complexity from the simplest beginnings. The first life forms were probably single-celled organisms similar to modern bacteria and archaea. For billions of years, that's all there was. Single cells floating in the oceans, slowly diversifying, slowly exploring different ways of making a living. Some learned to harvest energy from sunlight, others from chemical reactions. Some lived in boiling hot springs, others in frozen environments. Then about 2.7 billion years ago, something revolutionary happened. Cyanobacteria evolved oxygenic photosynthesis, the ability to split water molecules and release oxygen as a waste product. This changed everything. Oxygen is highly reactive, and for most of the life that existed at the time, it was toxic. We call this the Great Oxidation Event, and it was probably the first major extinction event in Earth's history. But some organisms learned to use oxygen, to breathe it, to extract energy from it far more efficiently than had ever been possible before. And these organisms, these early eukaryotes, they began to grow larger, more complex. They developed nuclei, internal structures, the ability to engulf and incorporate other cells. This process of endosymbiosis, where one cell lives inside another in mutual benefit, is how we think complex cells evolved. The mitochondria that power our cells were once free-living bacteria. The chloroplasts in plant cells were once cyanobacteria. We are, in a very real sense, communities of organisms that learned to cooperate so intimately that we became unified wholes. And from these complex cells, multicellular life eventually evolved. At first, just simple colonies of identical cells. But gradually cells began to specialize to take on different roles. Some became sensors, others became digestive systems. Still others became reproductive organs, division of labor, cooperation, the emergence of genuine complexity. The Cambrian explosion about 540 million years ago saw the rapid diversification of animal body plans. Suddenly, and suddenly here means over just a few tens of millions of years, the fossil record fills with creatures that have eyes, shells, segmented bodies, complex appendages. It's as if evolution was experimenting, trying out different solutions to the problems of survival and reproduction. But all of this complexity, all of this beauty, it's built on the foundation of those first stars, those first heavy elements forged in stellar cores billions of years ago. The carbon in our bodies, the oxygen we breathe, the calcium in our bones, all of it was created in the heart of a dying star, and scattered into space when that star exploded. We are quite literally made of star stuff. Carl Schwann said that. And it's more than just poetry. It's physics. The atoms that make up your body have existed for billions of years. They've been part of gas clouds and asteroids, part of the early Earth and ancient oceans. They've been recycled through countless organisms before becoming part of you. And when you die, when all of us eventually die, those atoms will continue their cosmic journey. They'll become part of the soil, part of new plants and animals, part of the ongoing story of complexity and consciousness emerging from the fundamental laws of physics. There's something both humbling and exhilarating about this perspective. We're not separate from the universe. We're part of it. We're the universe becoming aware of itself. Matter organized in such a way that it can contemplate its own existence, its own origins, its own ultimate destiny. And that awareness, that capacity for contemplation, it's perhaps the most remarkable thing that's emerged from our cosmic story so far. Think about it. Think about the journey from those first quantum fluctuations in the primordial vacuum to you lying here, listening to these words, capable of understanding them, capable of wondering about your place in this vast cosmic tapestry. Consciousness is, well, it's one of the deepest mysteries we face. We don't really understand how it arises from the electrochemical activity of neurons. How subjective experience emerges from objective physical processes. But we know it happened at least once here on Earth. And if it happened once, the question of whether we're alone in the universe has fascinated humans for centuries. Are we the only conscious observers in this vast cosmic arena? The only witnesses to the beauty of supernovas and spiral galaxies, and the dance of distant worlds around alien suns? The numbers suggest we shouldn't be. There are hundreds of billions of stars in our galaxy alone, and hundreds of billions of galaxies in the observable universe. Many of these stars have planets. We know this now from missions like Kepler and TESS, which have discovered thousands of exoplanets orbiting distant suns. Some of these planets are in the habitable zone, that sweet spot where liquid water can exist on the surface. But the existence of potentially habitable planets doesn't guarantee life. And the existence of life doesn't guarantee intelligence. And the existence of intelligence doesn't guarantee technology. And the existence of technology doesn't guarantee communication across interstellar distances. Each step in this chain from planet to life, to intelligence to civilization, might be incredibly unlikely. This is the essence of the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" If the universe should be teeming with life, if intelligence should be common, where are all the radio signals, the megastructures, the signs of vast technological civilizations? Maybe we're looking in the wrong places, or at the wrong times. Maybe civilizations tend to destroy themselves before they become detectable across interstellar distances. Maybe intelligence is far rarer than we think. Or maybe advanced civilizations transcend physical reality in ways we can't imagine, becoming invisible to our searches. Or maybe we're among the first. Maybe we live in a young universe where intelligence is only now beginning to emerge. The cosmic perspective tells us that we exist at a very special time. Not too early when heavy elements were scarce and planets rare, but not too late when star formation will have slowed and the universe will have grown cold and dark. We live during what astronomers call the stelliferous era, the age of stars. This epoch began a few 100 million years after the Big Bang and will last for perhaps 100 trillion years. We're actually quite early in this era. The universe has only existed for about 13.88 billion years, but stars will continue to shine for thousands of times longer than that. After the last stars burn out, the universe will enter the degenerate era, dominated by white dwarfs, neutron stars, and black holes. Eventually, even these will fade or evaporate through Hawking radiation, leaving behind a cold, empty universe of elementary particles and photons, growing ever more dilute as space continues to expand. But that's so far in the future that it's almost meaningless on human timescales. The sun will engulf the Earth in about 5 billion years, long before the universe grows cold. Our galaxy will collide with Andromeda in about 4.5 billion years, creating a new, larger galaxy that astronomers have dubbed Milka. These cosmic timescales they're difficult to grasp. If the entire history of the universe were compressed into a single year with the Big Bang on January 1st, then the first stars would form in late January. The Earth would form in early September, and all of recorded human history would fit into the last few seconds before midnight on December 31st. We are incredibly recent arrivals in this cosmic story. And yet, in our brief moment of existence, we've managed to figure out so much about where we came from, how we got here, what our place is in the grand scheme of things. We've mapped the cosmic microwave background, detected gravitational waves, peered back to when the first galaxies were forming. The James Webb Space Telescope is showing us galaxies as they appeared over 13 billion years ago, when the universe was just a few % of its current age. We're literally looking back in time, seeing the universe as it was when it was young and full of rapidly forming stars and galaxies. It's like finding baby pictures of the cosmos. And closer to home, we're discovering that our solar system is far more dynamic and interesting than we ever imagined. Mars once had rivers and lakes and might still have liquid water beneath its surface. Europa and Enceladus, moons of Jupiter and Saturn, have subsurface oceans that might harbor life. Titan has lakes of liquid methane and a complex organic chemistry that resembles what Earth might have been like before life began. The search for life beyond Earth has become one of the most active areas of scientific research. We're looking for biosignatures, chemical signs of life in the atmospheres of exoplanets. Oxygen combined with water vapor or methane in disequilibrium with its environment, or other chemical combinations that are difficult to explain without biological processes. The upcoming extremely large telescopes, ground-based instruments with mirrors 25 to 40 meters across, will be able to directly image some nearby exoplanets and analyze their atmospheres. We might within the next few decades find definitive evidence that life exists elsewhere in the universe. And if we find that life is common, that intelligence is not unique to Earth, it will fundamentally change how we see ourselves and our place in the cosmos. We'll know that the emergence of complexity and consciousness is not a cosmic accident, but perhaps an inevitable consequence of the laws of physics playing out over billions of years. But even if we are alone, even if intelligence is so rare that we're the only conscious observers in our observable universe, there's something profound about that too. It would mean that we carry an enormous responsibility, not just for our own survival, but for bearing witness to the beauty and complexity of existence itself. The responsibility of consciousness, if we are indeed rare or unique, is staggering when you really think about it. We might be the universe's only way of understanding itself, of appreciating the elegant mathematics that governs the dance of galaxies, the nuclear physics that lights the stars, the quantum mechanics that allows matter to exist at all. But let's step back and think about what we mean when we talk about the universe starting from nothing. Because there are different kinds of nothing, aren't there? There's the nothing of empty space, which, as we've discussed, isn't really empty at all. There's the nothing that might have existed before time itself began, if such a concept even makes sense. And there's the philosophical nothing, the absolute absence of anything, including the laws of physics themselves. Some cosmologists, like Lawrence Krauss, argue that our kind of universe, a universe with positive matter energy, balanced by negative gravitational potential energy, might actually sum to zero. The universe as a whole might be the ultimate free lunch, a quantum fluctuation that doesn't violate conservation of energy because the total energy is zero. Others like Stephen Hawking have suggested that the universe might be completely self-contained with no beginning or end, just existing. In this view, asking what came before the Big Bang is like asking what's north of the North Pole. The question itself might be meaningless because time as we understand it began with the universe. But these are ideas at the very edge of human understanding where science begins to merge with philosophy and metaphysics. We're probing the deepest questions that conscious beings can ask. Why is there something rather than nothing? What is the nature of existence itself? Are the laws of physics necessary, or could they have been different? The anthropic principle suggests that we observe the universe to have the properties it does because only universes with these properties could give rise to observers like us. It's a kind of cosmic selection effect. We find ourselves in a universe compatible with our existence because we couldn't find ourselves anywhere else. But this raises its own questions. If there are indeed multiple universes, a multiverse where every possible set of physical laws is realized somewhere, then our universe's apparent fine-tuning for life and complexity might be explained. We just happen to live in one of the universes where the constants are right for stars and planets and chemistry and biology. The fine-tuning it's quite remarkable when you examine it closely. If the strong nuclear force were just a few % weaker, atomic nuclei wouldn't hold together, and there would be no atoms heavier than hydrogen. If it were a bit stronger, all the hydrogen in the universe would have been burned to helium in the first few minutes after the Big Bang, leaving no fuel for long-lived stars. The electromagnetic force, the weak nuclear force, even the cosmological constant that drives the current acceleration of cosmic expansion. All of these seem to be set to values that allow for complexity, for structure, for the possibility of life as we know it. Change any of them by much, and you get a universe that's either too simple or too chaotic for anything interesting to happen. This has led some physicists to speculate about eternal inflation, creating a landscape of different universes, each with different physical laws. Others propose that our universe might be the product of some kind of cosmic evolution where universes that can create black holes produce baby universes with slightly modified laws. Lee Mullen has suggested this kind of cosmological natural selection where universes that are good at making black holes also tend to be good at supporting complexity and life. It's a fascinating idea, though, difficult to test with our current understanding and technology. But perhaps we're overthinking this. Perhaps the mystery isn't how something came from nothing, but why we expect nothing to be the natural state in the first place. Maybe existence is more fundamental than non-existence. Maybe being is more basic than non-being. The ancient Greeks puzzled over these questions too. Parmenides argued that change and motion were illusions, that only being truly existed. Heresitis countered that everything was in constant flux, that you couldn't step into the same river twice. These debates, these fundamental questions about the nature of reality, they're still with us today, encoded in the mathematics of quantum field theory and general relativity. And what's beautiful is that we can actually test some of these ideas. We can build particle accelerators and collide protons at energies approaching those that existed in the first moments after the Big Bang. We can detect gravitational waves from colliding black holes, ripples in space-time itself that carry information about some of the most extreme events in the universe. The LIGO detectors have opened up an entirely new window on the cosmos. When two black holes spiral into each other and merge, they create gravitational waves, distortions in the fabric of space and time that travel at the speed of light across the universe. These waves are incredibly weak by the time they reach Earth, changing the length of a 4-kilometer laser beam by less than 1,000th the width of a proton. But we can detect them. We've detected them dozens of times now. And each detection tells us something about the population of black holes and neutron stars in the universe. About the nature of gravity in its strongest form, about the history of star formation and stellar evo.